Thanks a lot. So yeah, it's a pleasure to be here to give these lectures. So that's going to be lectures about non-equilibrium system, non-equilibrium quantum field theory. And so what I'm going to talk about are essentially two things, as I was saying, I think, in the abstract. So I'm going to talk about non-equilibrium stuff, so NE. And the first thing would be steady states. So these are states, and I'm going to look at the averages and all that, which are stationary, which are out of equilibrium. I'm going to discuss a bit what it is. And then non-equilibrium fluctuations. So if you look at states is one type of thing where you have averages, and fluctuations is a bit more information about the states. Okay? So that's kind of two different subjects, which gives kind of more and more information about the non-equilibrium properties and of the many-body systems and all that. And the idea here is that I'm going to kind of use CFT as a very nice, simple example of quantum field theory out of equilibrium, where you can do a lot of nice calculations and you see quite a lot of physics happening. And also go to integrable quantum field theory. In fact, I'm not going to go too much over the details of integrability now, because that's very technical. But just with CFT and with free fermions, one can actually relatively easily get into integrable QFT. So I'll discuss a bit, how that works. So I give kind of simple examples of these things, and the same thing here. So for these two subjects, I'm going to use these as examples. Okay. And I'll start. I think my plans first 2 hours is to do just steady states, and then the last two to do the fluctuations. Okay, and give you the general ideas. Okay. So I start with general ideas of non-equilibrium. So by the way, just please stop me at any point if you have any questions. So, and in fact, I start with even equilibrium, right? If I talk about non-equilibrium, first I will just start about equilibrium. So what is equilibrium? Right? So if I tell you here's a many-body system, it can be a CFT or something else, and I tell you it is at equilibrium. So what does that mean that it is at equilibrium? Entropy is maximum, actually. So this is very good. Why don't I actually do this little calculation? So I can, I have some density matrix, maybe something that represents the quantum system, right? I want to maximize entropy. So I'd like to look at trace of rho log rho, right? So this is with a minus sign, that would be the von Neumann entropy, right? And I'd like to maximize it, right? But in general, in these many-body systems, that the energy is conserved. For instance, you maximize it with fixing the energy, for instance, right? So you put some Lagrange parameter, maybe you put some beta times rho, and then some Hamiltonian, which represents the energy, right? So that's trace of rho h will be the average of the Hamiltonian. And maybe there are some more conserved quantities. In fact, what I'm going to think about is maybe there's a few conserved quantities. So I have sum over I, some beta i's, and qi. Qi are the conserved quantities, whatever they are, available in the system. The Hamiltonian, maybe the number of particles, though if we do relativistic theory, not number of particles, maybe the momentum, some higher conserved quantities, right? And certainly I should also normalize the density matrix. I put the Lagrange parameter for the normalization. Trace of rho should be 1 for the Lagrange parameter. In fact, I should put trace of like that, gamma rho minus 1. Anyway, so then this is my entropy, and I try to optimize it. So I put delta of this equals 0, and I look at variation of rho, right? So this is just a very simple calculation to get something that you know very well, by the way. It's nothing very, very deep, right? I just do a delta of that. Delta means I vary rho. You can think of that as varying rho as an operator. It's okay. That will work as well in a quantum system. Or a classical system is just a probability distribution, okay? And you want this to be 0. So what do you find, actually? What you find a relation. Delta of rho log rho is essentially, rho is essentially log rho. So you find a relation that tells you what rho should be in order for this to maximize. In fact, what you find is that rho should be the exponential of minus beta I qi. And here you see I use the Einstein notation. There's the I and I there that are repeated sum over all conserved quantities. Okay, and there's one over z for the normalization. And so I told you, well, okay, the betas are such that the energy is fixed to something, the momentum is fixed to something, and all that. So in fact, this is my rho, and then I choose the beta such that the trace of rho times the h is whatever energy that I number that I wanted to fix energy to, right? Or in fact, marginally trace HQI is whatever, how do I call it? Well, whatever numbers that I want for the concept quantities. So there's a relation, right? So betas are fixed by these numbers and vice versa. Okay. So what is that? So these are called the Gibbs states, right? So this is equilibrium, essentially. That's you said the maximizing entropy. That's just perfect. That's what I want to say. So equilibrium. Now, actually, there's a few ways of understanding equilibrium. Actually, so if you think about that, okay. So usually, I put here usually. I put e to the minus beta. I mean, one will see in the book something like e to the minus beta h, where h is Hamiltonian. It's a derivation like that where you just put one constant quantity, right? But I could as well put the total momentum, which is also conserved, right? It's minus beta h, and perhaps plus I put here maybe minus vp or something like that. So, something like this. Okay. So this is but it's not quite a Gibbs state, right? It's a bit different. Still, it's perfectly fine for maximizing entropy. Well, there are different ways of defining equilibrium. Maximizing entropy is pretty good, but somehow, I mean, one of the ways that people talk about equilibrium is very often by saying that the state is time reversal invariant. Time reversal invariance is kind of an important concept. Why time reversal invariance? Well, somehow at equilibrium, if here the environment is at equilibrium and I look at what's happening at a given point, well, nothing moves. There's no currents. There's no current of particles or energy or things like that. But if I put a momentum there, then there will be non-zero current under that density matrix because that momentum breaks time reversal invariance, and then you don't have conditions that say that the current of energy is zero, right? If you have time reversal invariance, the current of energy must be zero, but if not, it's not necessarily zero. So usually for equilibrium, in fact, what one would say is that you have time reversal invariance. It's a bit I don't know, ideological maybe. I mean, it's not so fundamental, but it's usually what's happening. And then that means that this V should be equal to zero. Okay, so something like that. So you look at your conserved quantities, and those that are not time reversal invariant, you got to put them to zero. Why not? Okay, but it's just a bit of nomenclature. It's just kind of okay. That would be equilibrium. It's important because when I talk about non-equilibrium steady states, actually, well, some of these actually have the form of Gibbs states now but they are not time reversal. So the point is they will not be time reversal invariant. Okay. Okay, so this is kind of some general concept. Another kind of a general concept here about equilibrium and states. So there's this thing of maximizing entropy.
External magnetic field.
Yeah.
Or if your system has magnetic order.
Yes.
Break.
That's correct. That's correct. Yeah. Well, sometimes, you can have these constant currents of, exactly. So you might have, and then is this equilibrium or not? Yeah. Okay. You can define as you wish. If you want to see this is equilibrium, I'm also happy with it. Actually, it's fine. But so it is interesting because people talk about non-equilibrium steady states, and now it's kind of special thing, right? Non-equilibrium state. But perhaps what I want to say is that, well, we'll see, it's not necessarily such a special thing. The one thing special is the breaking of time reversal invariance. And then you have systems where this is broken automatically. Well, okay, so maybe so this is kind of maybe they are in non-equilibrium steady states as well, right? And still, and then there are, yes, yeah. So time reversal invariance is a very good question. So time reversal invariance is going to be in evolution of the operator algebra, so precisely an evolution of the algebra of observables, which is anti-unitary, and should I say something else, which is anti-unitary and which preserves the energy density or the stress energy tensor. Sorry, commuting you mean here? Yeah, sorry. So yeah, these were I should have written that. So QI commute with the Hamiltonian because they're conserved quantities. Because I want to fix the conserved quantities. Sorry, I should have said that. Thank you. Yes. But that does not mean that they are invariant on the time reversal symmetry. Yeah. So T is something that is anti-unitary, and it's an involution, and it preserves it's a symmetry of the operator algebra, so it preserves the algebra of observables. And so if I should think, so what are the properties that I would want, but I think you also want that it actually preserves the Hamiltonian. Then by this, of course, it makes T2 minus T, because in quantum mechanics, you have e to the ith. So it works. Okay? And I think you can convince yourself that that should give rise to P goes to minus P, if I remember correctly. Yes. Consider P to minus P, yes. So I don't remember exactly how I decided to do it, but maybe if I write a bit more, we're going to get to that, and then we can rethink about it. Okay. But yeah, so it should be, I mean, in the end, the momentum is essentially, coming from a time derivative of the energy, and so that gives it the change of sign on the time. Okay, so that should be the case. Okay. But it's a bit actually how you define your time reversal symmetry. So it's a bit up to you. Like symmetry, you can define them a bit, up to you. So that's why perhaps this definition is not so fundamental. That is more fundamental. Yeah. So indeed, so let's we have conserved charges. Let me write them as integration over conserved densities. This is my notation is conserved density, energy density, maybe spin density, momentum density, etc. Okay. And since dt qi is 0, then what you should have is a continuity equation for the density. So the total integral over x of dt qi is equal to 0. If the total integral of a local observable is 0, that local observable should be a total derivative. In fact, that kind of even general proof of that within some many-body systems. That means that you can write dt qi plus dx ji for some current equals 0. This is like Noether currents, right? Continuity equation. Right? And so these are the currents. And then what you ask is, what is the average within that density matrix of these currents, within density matrix rho, right? And the question is this, or should you have a non-zero current or not? And so if, for instance, if you take if time reversal invariance of a conserved quantity, say of the Hamiltonian, which is Q0, the Hamiltonian density. Okay. This Hamiltonian density is time reversal invariant, natural definition of time reversal. Then by that equation, it would imply that the time reversal invariance of the current is minus the current itself. And so if the state is time reversal invariant, the current will be 0. That's conventional idea. Yeah, so but I'm thinking about conserved quantities, extensive conserved quantities that have a densities and then therefore as a consequence where there's a continuity equation. And these currents. Spin system, if you have a spin chain, for instance, XXZ spin chain, that is correct, that holds. For the spin, for instance. Spin is conserved will satisfy this equation. Complete generality, any local many-body system, in fact, even theorems for quantum spin chains, okay? If you have a local observable, so, which is like dtqi, whose integral is 0, then there exists a local observable J such that this equation holds. It's kind of completely general in anybody in quantum spin chains that can be actually shown from. Yeah, spin current as well. There will be something like that. I mean, if it's a, but okay, let's not go into details. Maybe you have something more complicated in mind with this. Yeah, if the Hamiltonian is local, then that comes out. Yeah. Other questions? Yes, go ahead. Well, here I'm not really thinking about time scale. This is just a level of observable, like operators, and it does, a fixed state. I'm not really doing I'm not letting things thermalize or things like that. That's another question, actually. That's another thing. Yes, indeed. So this is indeed a very good question. Yeah, I agree. So this is a local observable, like microscopic exposure. What you have in mind is on-cycle currents. So currents you would obtain at long time on average, and then see, for instance, how these change if you change the force, external force and all that, and have on-cycle relations and all this stuff. And then you have diffusion and all that. And that's, okay, I won't go too much into that, but this whole theory that is based on that, actually, right? So basing on this fundamental, microscopic stuff, you can get to on-cycle current and on-cycle relations. but it's a different thing. It's a different lack of time reversal invariance. It's because of thermalization, and it's a many body effect. Different thing. Yeah. So here's the macroscopic thing. Okay. But so yeah, yes. So okay, the structure that so this is a many body system, some conserved quantities, some conservation laws, and some averages of these densities and these currents within a set of states. And I'm thinking about that type set of states, right, where you have Lagrange parameters for every conserved quantity. Conserved quantity, I think of them like that, so extensive with local density. So it's kind of general setup. And you can think of these as your equilibrium state. You might ask or not to have time reversal invariance. But yeah. Another question. So one thing that is actually quite important is that, when we think about states now that and density matrix, but actually I'm going to think about infinite systems, infinitely large systems, right? 1D, okay? So in infinite system, the density matrix, it becomes an infinite matrix, right? And you have to control the infinity and all that, and it's a bit tricky. So the typical thing, in fact, for determining what a state is, and that's going to be important, and we're going to talk about, is just think of a state as something that gives you averages of observable. It's fine, a density matrix give you averages of observable via the trace formula, trace of rho times something, right? But if you are an infinite system, you don't have density matrices anymore, but you can still have averages of observable, at least local observable, right? So you can think of that as a limit when the volume goes to infinity of a trace of a density matrix for finite volume and anything else there. Now that limit might or might not exist, right? But typically in many body systems with local interaction, if you take states like that, the limit exists for every local observable. Limit exists. And that's your state. That's give you averages of local observable. It's a useful way of thinking. And it's useful kind of conceptually, it's a useful way of thinking. Let's say. Okay. Now let me do a bit more explicitly what I mean by non-equilibrium steady states now. So what are the questions one would like to ask? I mean, you can do that, you can maximize entropy and all that, but that's not, well, what you would like to do perhaps, it's a bit what you have kind of stated, that you'd like perhaps to have an external electric field or force or something like that that will generate a current, and you want to describe what the state is now. Okay. Now, in fact, there are different ways of generating a non-equilibrium steady state. And external electric field, now that is good, I could do that, but there's another, perhaps more fundamental way. So instead of having an external force, you can have an initial imbalance. It could be similar, right? So you can have a lot of high temperature there and low temperature there, and let the whole system evolve. And that's nice because then you can evolve it in a unitary fashion. So you don't have to have some external force perhaps that changes in time. It's just, your initial state is something and then you let it evolve in time. Okay? So this is the partitioning protocol for non-equilibrium steady state. And it's pretty useful tool to study what non-equilibrium steady states are, what form they take, and get their general properties. So for me, it's going to be a tool. It's not the full thing, but it's a useful tool to study non-equilibrium steady states. And I'm going to discuss the physics of that and see what we can calculate in there and see what the steady states coming out, what properties they have. Okay. That's kind of an interesting thing. So that would a bit answer your question. Okay, if you put a magnetic field, well, I'm just thinking about Hamiltonian, maybe with some nice simple properties. But I'm putting things out of equilibrium not by an external force, by initial imbalance. Okay. So what I have, I have some system with some left temperature and some right temperature, which are different. For instance, T left greater than T right. Okay. Then I let the whole thing evolve unitarily. And my Hamiltonian, for instance, is time reversal symmetric and everything's fine. So it's not from there that I have the breaking of time reversal symmetry now, right? Just let it evolve. Okay. So in explicitly, what I would write is so I let it evolve, and then here I look at some observable at say 0.0, t. So look at whatever observable, right, and see what happens at very large time. Okay. So in equation, I'd like to take the limit when t goes to infinity of, well, that initial average there, where L has already been taken to infinity, okay? But I'm going to write it as a trace, but okay, I'm thinking of L having been taken to infinity first, and then to infinity, okay? Trace, and then dimensional density something like that, minus beta L, the left bit of the Hamiltonian minus beta right times the right bit of the Hamiltonian. Okay, this is my initial density matrix, and then I evolve the operator. So I put O 0, T and 1 over Z. Okay. So this whole thing is that L goes to infinity. Okay. So that's first limit and the other limit afterwards. This O 0, T is just the one evolved with the full Hamiltonian. Okay. Now, so I have three. So my full Hamiltonian is H left plus H right. There may be some little interaction between the left and the right because you want to have, my initial state is like separated like that, but the full Hamiltonian has particle that goes from left to right now. So there's some little interaction between left and the right there. Doesn't matter too much. And so this is my initial density matrix, and O, of course, is evolved with the full Hamiltonian, with the IHT, O at 0 to the minus IHT. So this is the partitioning protocol, and question is, yeah, so what is the give? Actually, yes. Yes. The other one was like, I should just take it away. Just here, I want to evaluate that operator at 0, T. That was part of the graph. Yeah, something like that. Sorry about this. Right? No. Yeah, so indeed. So the question, what do we expect actually? If I do that with 2 bars of metal and I connect them to each other, what do I expect? Thank you, yes. So in the sense, I don't want to put currents already in initial state, right? So it's equilibrium and my Hamiltonian is time reversal symmetric, simple as possible, right? And then what happens if I do that? So if I have 2 bars of metal, 2 half bars, and connect them suddenly, let them evolve. So, we know what happened. It will slowly diffuse, right? Is the heat equation 4 years now, right? So it diffuse, and we'll get to something where this was the heat equations. You have dT. So you have kind of a dT of temperature will be proportional to dx square of the temperature. So this is the temperature T, yeah. That will be the heat equation. And then if you go to very large time, the x derivative will be very small. Temperature, will not evolve so much. And in fact, things will just thermalize out and get nothing very special happening. Okay. But if you do that, not with temperatures, but with bags of water, you have a big bag of water with an interface. They have a lot of water there, and it's infinite, right? And then you have no water there; it's infinite. And then take away the interface, water will start flowing. What's going to happen over a long time? Yeah, you're going to have a river flowing. It will not stop. It will just go. Right? Maybe eventually it will stop because of the friction effect, whatever. But it essentially will just go. So there are 2 possible things, and this water thing is more a conservation of mass, right? You can write dt rho plus dx v rho equals 0, where rho is the density or perhaps the height of the water or something like that. Okay. So there are 2 different types of equations that can control that. In fact, what it changed, it depends if the system is ballistic or not. If the system has ballistic modes or does not have ballistic modes. Okay. And for that, that depends on the structure of conserved quantities nowadays. And what I want to give you examples. So this is kind of ballistic, purely diffusive. Okay? The result is very different for the large time steady state if it's ballistic or diffusive. Right? And what I want to give you is an example where you have ballistic. This is what we're going to be studying. So with the CFT and with integrable models, you have ballistic propagation. And then you have non-trivial, non-zero currents emerging at large time in the sense of, so this is my stationary average, okay, which is this limit. So average stat for stationary, STAT for stationary. Okay. This is that limit that gives me stationary average. And so in CFT, this state, the stationary average, is non-trivial, current carrying, out of equilibrium, time reversal, non-symmetric. Now that stuff, even when you start with time reversal symmetric, equilibrium, 2 half now. So this is a way of generating a steady state. Okay. I just want to do a small calculation that show you what happens in CFT, and we see what happens. And then say I start with the CFT, then generalize, and we see a bit more how, what does it mean that it's ballistic, how it arises, okay? And what are the kind of main properties of these non-equilibrium steady state. Okay? So this is the thing. So what about this state, obtaining that limit, which is physically relevant now? What are these states? Are they really non-equilibrium steady states, and what structure do they have? So, or was it lost on now? Yes. So these are the initial state, just initial state. I put different temperature. I separate my Hamiltonian between left and right in some way. Then I just let the whole thing evolve. With the Hamiltonian H that doesn't know about beta left and beta right. It's just the Hamiltonian of the system. That's it. And see what happens very large time. So this is it's actually rather non-trivial problem that people have been studying for quite a long time, actually. From the 70s, even in the context of studying non-equilibrium steady states. There was first few results about that in the 70s, like non-trivial results. Was by Spohn in the book that's in the harmonic oscillator, where they found what the state was now that. And now we understand much more the whole thing was happening. Okay. Even before that, Riemann in the context of fluid dynamics studied that, I guess, the Riemann problem, yes. So you see, I don't want to have an external reservoir with some weird interaction with a kind of an arbitrary reservoir that I don't know how to describe, but I could do it like that, yes. I mean, in the context of impurity problems in condensed matter, people think about that by putting here a free fermion reservoir at left temperature T and a free fermion there, and some non-trivial kind of a fine dimensional quantum system connected to fermions, and then the reservoir puts heat and gets the heat out and all this. And this is realizable in experiment. Even it's a good representation of what's happening in experiment. So these, in this context, these are really truly reservoir, like the battery you put in your experiment. It's really that. Yes, indeed. Okay, I can think of it a bit as a toy model, right? And do whatever many body systems that I'd like to do for that. Because the initial one, thermal one, is not the full Hamiltonian, is the left bit of it and left part of it. When I separate these two, I have to disconnect the chain, whatever. There's missing one side there. They're different, In the bulk, far here, they're the same. They're the same. The bulk, they're the same. But around there, so what can you expect, right? So you have this impurity, well, this initial disconnection there, and then you could expect that, okay, there's a T left and T right. Of course, if you go in time, I go downwards now in time, far here, you're still going to have T left because we know influence of the impurity, right? Of the initial disconnection, it's like an impurity. But then there will be some slow change, and then maybe some current or something like that, and far here will still be T right. But here is going to be some supposedly stationary state. If the limit exists, it's going to be stationary. And it will change perhaps slowly from there to there. How does it change? What's the profile of current? Things like that. So yeah, this, yeah. Yeah. So this is in the exponential. Yeah, and this is just the average within it. Oh, sorry. Yes, indeed, correct. This is not in the exponential, correct. Yeah. Okay, so this is like becomes a bit model dependent, right? What is delta H? Depends on the model. You can implement that different ways now. So you have to take a model. I can take a CFT and then, but yes. So you see, this is, if I add a delta H there, first of all, I wouldn't know which beta to put to the delta H, right? Because it's beta left or beta right. I can add something, but it still will not be the full Hamiltonian, right? So this still will not be time invariant of the time translation. This is not stationary. Whatever I do is not stationary. So it cannot, on the left side will stay T left. And on the right side, very far will stay T right for sure. It will not, yes, indeed, it will not change its temperature, right? Something will happen here. Will it equilibrate? Yeah. There, but the full Hamiltonian H is a. Yeah. Yes, for sure. Of course, yeah. The thing is, H with H left, is not zero, right? Because it doesn't have the H. Right. Yeah, because of that, it's crucial that yeah, it's totally crucial.
For mathematicians, so H left and H are going to be
Yes, yes.
There's no A.
Precisely, yes, precisely. That's how you could do it. I mean, it's a natural way of doing it. But this is non-zero. But this evolved. But the point is that the evolution is passed on some type of light cone, right? Because it's just the detail. So far from it, there's nothing. But here is something. Ballistic system. Indeed. And then in diffusive system, because of that, is some kind of square root. But sorry, I just broke that. But yeah. But in in quantum spin chains and in relativistic GFT, they're very similar. You can show that there's got to be a light cone beyond which nothing happens, right? This is clear. I mean, at least with exponential accuracy. And inside something happens, but then it's complicated. What happens inside? Okay, this can be a difficult question. Okay. All right. Now let me do the example of a CFT. I want to get to kind of more complicated examples eventually. Okay? And maybe I tell you already kind of the main thing, the main idea to solve these things is, well, ideas I think that people really hinted at already is hydrodynamics. So we said heat equation, there was a Sager currents and all that. So hydrodynamics is the thing that allows you to really understand what's going on, and hydrodynamics is extremely general. So I want to get to that, but first I do the simple example of a CFT. This is a CFT.
Say simple. So which CFT?
Yeah, so indeed. So okay, so CFT. Let's say I will do the simple bit of the CFT example. Okay, so CFT, it can be very complicated, and there's a lot of structure. And depending which observable I put there, a lot of things can happen. But I know in CFT, there's at least the stress energy tensor, right? So I have a T mu nu, which stress energy tensor, which has simple properties, which is always there, and which I can control, so I can consider that. And that's useful because I look at energy and momentum densities, which is physically natural. And this is very universal in CFT. So let me concentrate on that. In fact, that, surprisingly enough, has a lot of the structure of general many-body system already, for some reason. Okay, so I have a stress energy tensor, so some matrix. There's some. I use this notation. Yes.
So the space dimension is one.
Yeah, one plus one. Yeah, one space dimension, one time dimension. I could do those things in higher D as well in CFT. Yes. Yes, indeed. Maybe I get to that. That will be specific to 1D. Yes. What happens with D is not zero. Maybe not this section, maybe the something, yes. Indeed. So we can go for high D, but for higher D, you need to do something slightly different. Yes. But for 1 plus 1D, you can do it quite straightforwardly. So let me think of it. So this is 2 by 2 matrix. Okay, there's an energy density. So let me call it H. Okay, there's a momentum density. I call it P. There's an energy current in relativistic system. The energy current is the momentum density. Okay, so current of energy equals momentum density. This is, let's say, the definition of relativity. Kind of definition you can basically conclude everything that you need just from that, of relativity. If I was in a Galilean system, I would say current of mass equals momentum density, that is Galilean invariance. And what about the current of momentum? Well, the current of momentum in CFT, what is it? What do we have? We have, T mu nu equals T nu mu, so we have so maybe I should write this plus that. Yeah, I'm not sure if maybe I should write it like that. Yes, and then yes. Okay. So anyway, so T mu, and then we have T mu mu equals 0. So we have tracelessness in CFT, tracelessness. So that means that these two are related to each other. And if I put the indices correctly, then the current of momentum is just exactly equal to the energy density. So put an H there. So that's my, okay. So if I write the equations I have, this is dt of H plus dx p equals 0. And sorry to go over this kind of trivial stuff, but then it generalizes nice. I think these are two equations that I have, right? Conservation of energy, conservation of momentum. And then naturally I construct H plus P, which I call T, and H minus P, which I call T bar. And then D satisfies simple relation, right? So then T of x comma time becomes just a function of x minus T. That's the variable Z in real time, not in equilibrium. In real time, it's kind of real time CFT, right? And the T bar just becomes a function of x plus T. Okay, so that's kind of basic 1 plus 1 dimensional CFT. The only thing I'm using is the tracelessness of the stress energy tensor, so not a lot of the CFT for sure. Okay. So, but then this is a very simple time evolution, and I can solve exactly the problem that I have there. The problem that I have there, I can solve very very simply. I don't have to do a lot of calculation actually to do that, right? I want to evaluate T in the stationary state. So all I have to do is evolve the stress tensor for a large time at position 0. So this is kind of a limit when time goes to infinity of the average in my initial state of the stress tensor at minus T. So this is at 0, 0, right? Everything at 0. And then I just evolve it in times minus T, right? This is in my initial state. How do I call my initial state? I didn't call it anything, so let me call that rho, I don't know, 0 for initial state. 0. This is my initial state. So I take that evolution at large time. What's the result of that? That means I put the stress tensor at position minus T. Minus T is a position in space here, right? Because I use its right mover. So if I put an observable very large, on very large negative space position in my initial state, it's my initial state, what do I get? Large negative position. I don't even need to, I just told you this is a Hamiltonian. So I get thermostate, temperature beta left, or inverse temperature beta left, yeah? Together. So this is my initial state. On the left, it looks like T left. On the right, it looks like T right. That's it. I don't even need to take T to infinity. T0 plus is sufficient, right? Well, be careful because on the left is this H left, but this H left doesn't have the delta H. It's actually a system with a boundary, right? H left is a system with a boundary. But for the stress tensor, it doesn't matter. I can open it up. In CFT, the boundaries, you can just think of CFT with boundaries like a CFT on the line where you have a single kind of a single right mover, say a single polymorphic sector. Okay. But in any case, I can go very large. So what should I find? To find the average of the stress tensor at any position, doesn't matter, the limit exists, in a state which is thermal at temperature T left, or inverse temperature beta left. So this is trace exponential minus beta left, the Hamiltonian of the CFT, and T, and 1 over Z. Okay. And now this is not H left, this is H, because I've put my operator so far there that I don't see anymore. And this boundary, this is just the bulk Hamiltonian. Okay. So this is, what is that? Is this the result for that? Well, I can do the same thing for T bar in the stationary state. And what I will find is the average of T bar in a thermal state with temperature beta right. Okay. Now I know this is a thermal state. So in the thermal state, of course, so the average of the energy in thermal states is C pi over 6 times the temperature square. That's kind of a basic result of CFT. The average of the energy in thermal state. While the average of the momentum in any thermal state is 0 because it's equilibrium state, no current. And so that means that the average of T and T bar, these thermal states, is just C pi over 12 T left or right square. Okay, so I know the average. So I know then what all my observables are. I know my current and everything in the stationary state. So the energy in the stationary state then is kind of just average. So T left square plus T right square, C pi over 12. While the momentum, which is the energy current in the stationary state, now is non-zero. Because all I have to do is the difference of T minus T bar over 2. If I do my calculation correctly, T minus T bar over 2. So that becomes then C pi over 12 t left square minus t right square. This is the result for the energy and the momentum in that stationary state. It's not a full description of the stationary state, but at least for these observables, have that. In particular, the momentum is non-zero, so that means that the stationary state is not time reversibly variant, whatever it is. Okay. Yeah, calculations. It's kind of a trivial calculation, and sorry about this, but it encodes what's happening with it. Here, you have left and right movers, and then you have a non-trivial stationary state that gives certain value of energy and momentum. You see, this is my definition is that always stationary states where I define state as being things that give averages of observables. I do that, So forget about the rest of the system. Just take any local observables. Here is just energy and momentum. Okay, I could think of more things. In fact, one can do more things, but take energy momentum there in that state, defined as an infinite time limit.
Yeah, so for the time on the left hand side.
Yeah, so of course, I can put time t here, but it will not change anything because it's stationary. Exactly. So I put
one line right time.
Well, yeah, I mean, indeed, but if I could put 2-point function, I could look at the time correlation, for instance. Yeah, and here it will be relatively trivial. I mean, it's simple. But then I put t00, t0t, for instance, in the stationary state. Both are evolved in time, very large time, and you get a stationary limit that exists. So yeah, so maybe I shouldn't write that, but yeah, of course it doesn't matter at the time.
It's really going to be at the origin.
Yeah.
Very large time.
Yes, precisely. Yeah, precisely. Yeah. So it's whatever happens at very large time. I don't have to put origin. I can put anything else there. I can put any correlation function, whatever. But everything at very large time. In fact, I can even think more generally and put very large time in very large positions. Here I'm looking there, the stationary state. But I could look there as well, and there as well. So I can do all kind of limits, which are not necessarily the stationary state, right? And whatever limit I do, I'll see something fun. Now, this is just I have 3 here. 3 is too complicated for me, I think. No, the other one doesn't move. Okay. So I'm going to hide that then and continue. So there's more that I can do. I'm talking about the state. I just gave you averages of 2 observables, and you said, William, you can evolve the density matrix as well, right? I mean, one can do that in CFT. So the density matrix, it's very kind of trivial thing, but I mean, simple thing, but correct. So you have exponential minus integrations from minus infinity to 0, t x plus t bar x, and maybe I want to put over 2 in my normalization. Dx, that's the Hamiltonian density, and this is h left and multiplied by beta left. Okay, that's 1 bit of my initial density matrix, so rho 0, and the other bit is minus beta right over 2 integration from 0 to infinity of t plus t bar. Okay, that's the other bit. And then I can just evolve that in time, but the evolution of the density matrix is e to the minus IHT, rho 0, e to the IHT, right? So that's going to be my rho of t. Then I can evolve that in time. It's not too difficult to evolve that in time. The delta H, you see, it's the idea that I have this cut there at 0 and it's cut at 0. So actually, this is kind of a system of the half line. And I've already opened the top, so to speak, that system of half line with a boundary condition which is t equals t bar, and you can open it up and then it looks like on the line, and then it will look like that essentially. So I'm skipping some of these details here. Actually, it's half line system with the boundary condition t equals t bar. But it's okay, so I can write it like that. And then once I've written it like that, actually it's relatively simple. So it's relatively simple. So somehow the boundary condition is implicit in it. Then I can just evolve that in time by evolving the left mover and right mover explicitly as they are. Like this has been opened up essentially. So I should have probably done that more precisely, but let me do it like that for now. Okay. So if I evolve that in time, I get exponential minus beta left over 2. integration from minus infinity to 0, and I have t of what x comma, well, x that becomes x comma t, which is x minus t, plus t bar of x plus t. And then I also have the other bit, beta right over 2, integration from 0 to infinity of t of x minus t plus t bar of x plus t. So simple evolution, the details of the boundary condition a bit under the carpet, but this is, exactly, certainly this reproduces the right things on the bulk, right? If you're on the bulk on the left, that the Hamilton looks like that. So that is perfectly correct. And that's perfectly correct. Okay. So you evolve that in time, you get this. And now you can look at what happens for any local observable around the point 0 at large time. Okay. So you look at this density matrix. So at x equals 0, where you're going to have, well, this is an exponential now, but if you look at x equals 0, so here, that value there will always be smaller than 0. You will never get 0 here. But that value there will be, from minus infinity up to time t. That will include the 0. This one will include the 0. So that value will be inside, say, from minus t up to infinity, while this one is always greater than 0. Yeah. So the situation that I have is that maybe I can use some color. So I have, this is the space, and this is, where is my row of t supported? Where do I have operators? Well, there's one bit which is, so this is minus t, and that's t. Okay, the one bit with beta left, where you have something there, and what you have is a t, and with the beta left, and when you have something there, and this is t bar, also with beta left. And if I use a different color for the beta right, I have this, and this t with beta right, and this one t, yes, which is t bar with beta right. So that's the situation, and I want to look there. A little graphic, to see what's happening, left to right mover. So what does the state look like at 0 for any local observable? Is going to look like exponential minus beta left. T bar, so integration of t bar of x dx, minus beta right, integration of t of x dx. Now I put the integration over the full line. How can I do that? Well, I'm just looking at very large time around this point there. At very large time, these boundaries that are very, very far. So from the point of view of local observables, that looks like integration over the full line. Just for local observables, of course, not extensive observables. That's crucial. You look at the stationary state, it's not for any of those, for the local ones. If you take an extensive one, it's going to see much more, not just the emergent stationary state. It's going to see a lot of what's happening. The local one, we're going to forget a lot of things. So rho stat just will be one of these that. In other words, you thermalize the left mover or the left movers should be the right mover perhaps, beta right and the left. So one of them is thermalized by beta left, the other by beta right. Indeed. So I should get it right. You just let me know if I made a mistake in the direction somehow. But yes, H left is T bar, like that. I probably got it wrong, right? Ah, yes, of course I got it. Sorry. You should. Yeah. This is minus IHT here, minus IHT, right? When I do that here, this is for the usual evolution of a local observer plus IHT. It's the opposite, right? So this is a plus and that's a minus. So, or maybe I should say minus and plus, and this is T bar and that's T. T bar and that's T. Because this is, is the other picture, right? When you evolve the observable or evolve the state, right? You evolve into different time direction. Okay? And so indeed, this is the opposite. Yeah. That's T bar T and T bar and t. And then is the opposite. So this beta right. Now it makes physical sense, beta left. So you see that the right movers are terminalized with beta left, and the left movers with beta right. Now, does it make sense indeed physically? The picture is that I have, my initial state there, t left, t right, and then I look there, and if this is a right mover, then as it goes in time, it goes towards the right. So it just, it will just measure stuff that comes from the left. That's the opposite. If this is a left mover, well, you will see stuff that comes from the right. So this is my state and has natural interpretation. You look at that, if it's the right mover, you see stuff from there or see stuff from there. It's the idea actually of kind of, well, it's very simple because it's 1 + 1 DCFT, where you have somehow these left and right, separated left and right modes that propagate from your initial state, and that gives everything about what you see there at the time. If you just see the holomorphic sector, well, you see from there. If you just see anti-holomorphic sector, you see from there. If your observable is non-trivial, not factorizable, holomorphic, anti-holomorphic, you have to think a bit more carefully. But let me concentrate on the VRZero subsector of observables, and then this is sufficient. Okay, questions about this? So this is kind of the stationary state. Yeah. So importantly, maybe so. Okay, so I should say a bit more then. You see, this is my initial state, h left. If I were to evolve with h left, what happens? Well, that's not true anymore. Okay, if I evolve with h left, okay, let me do the little picture, maybe in the corner here, a little picture. Okay. This is my half space, h left. Okay, have some stress energy tensor there. I evolve it, so it's I put that like that. Okay, it starts, it's there. It starts, it goes to the right. It's the right mover, right? And then it goes to the boundary, and it reflects and gets into a t-bar. That's the evolution with the h left. The h left evolution. Now I evolve with h. I look at this t. I did not transform it into a t-bar. It went through. So when I wrote t, x minus t, t, x plus t, this one actually, I went through the boundary there. And that's because I evolved with h and not h left. That's the lack of commutation relation now. Okay? So this is different. That is okay for evolution with h left, but it is not okay. That's not an h left evolution. That's an h evolution. H left, I would have actually this bit of t bar that's missing. I would have, that bit there would have been just a bit like that. So I would have just filled this in and then back to h left. Again, h left is invariant under itself. Yeah, h left, yeah, exactly. But in conformal field theory, the only conformal boundary constraint in the Variance sector is t equals t bar, right? That's the boundary constraint you must have. For the Variance sector is the only thing. You don't have any. No, but you care because when you evolve with h, you don't have that sharp boundary anymore, and that's why then you have this extending all the way there. The time evolution does not have any boundary. It's the initial state that has a boundary. But the only way I put the boundary is zero there. But the evolution with h left, would involve that reflection, but not with h, because h is on the full line. So that's why this goes further, and that. So here we actually see this. It's an excellent question, right? Here we actually see the effect of the delta h. The delta h is what allows you then to further, and then you have. So this is that's kind of the solution. Now I wanted to finish with this, but I want to say one more thing. I guess it's kind of time to go, but essentially that's what I wanted to say. It's been 1 minute before beyond. I mean, I started with maximal entropy states, right? Then I get that state, where is it? That state. Okay? I can rewrite that state in a nice way, and that way is as exponential of minus. I can put beta left plus beta right over 2 times h t plus t bar plus something that has momentum. So the total h integration of t plus t bar plus momentum, and the momentum will be some velocity times momentum, and the velocity, it's not a velocity, it's a velocity, and velocity is going to be something like beta right minus beta left, I guess you should put a minus, over beta right plus beta left. just putting these two terms together, right? T plus T bar. So actually, this is just one of these density matrices that had a beginning with the concept of quantities, the Hamiltonian and the momentum. So maybe you can say it is equilibrium, but obviously it has currents just because there's a momentum. In fact, all it is, it's a relativistic boost of a thermal state. So because if you boost a thermal state, you add to H a momentum operator. It's a boost by an appropriate kind of a boost parameter, which you can calculate with a boost velocity, which is that's the velocity essentially. And the rest temperature that you boost is actually the geometric average of the left and right temperature. If you do the calculation for the boost now, that is the geometric average, not the arithmetic, but geometric average, the square root of if you do calculation. So actually, this is a boost to thermal state. So back to the beginning. Well, this, yeah. So maybe it's a non-equilibrium state, or it's not, but certainly has currents and comes out from this non-equilibrium situation. Okay. So yes, that's it. Yeah, one can see that it has a. Okay, one can do the whole space thing. So if this is time equals 0, this is time. There's a light cone. In fact, what you see is a stationary state. For the point of view of this Virasoro subsector, you see stationary state everywhere, T left on the left and T right on the right. So there's a sharp change of state from the point of view of the Virasoro sector. It changes sharply just because of this separation between left and right mover. And that's the situation then in 1+1 DCFT. It's a similar situation more generally with some changes, which I'm going to explain in the next lecture. So next lecture, I'm going to introduce then the idea of hydrodynamics. So CFT is very simple, but we see explicitly what's happening. We can construct the stationary density matrix. We see that there is a current and all that. But in general, we don't have so much control over all of these time evolution, right? It's hard to do time evolution of local observables in TFT, right? And but a good concept to use is hydrodynamics, and this is kind of a baby example of what's happening in hydrodynamics. Yeah. It's a very good question. In fact, CFT is a little bit degenerate actually, because CFT officially it is integrable. The Virasoro sector has infinitely many conserved quantities, so I could have put all of these things, right? And in fact, even I could have expected that what happens there at large time something more general than that. There's all these conserved quantities, right? It turns out is this, okay? So yes, I can put marginal like T square, like other conserved density there with higher temperatures, T square, T cube, and all that stuff, and do the calculation. And I'm going to have actually, because it's so simple here, a separation between the left and the right movers for T square, T cube, and all that. All the conserved charges still separate, yeah, because it's so simple. But in general, is not the case. In general, you start with something on the left and on the right, it can be a GGE, thermal, and all that. You evolve, and what you get to is going to be something a bit like that, but that involves, in general, all of these conserved quantities. And then the point is, what are the coefficients that are involved there? So the general thing is exactly this. You need to consider all the conserved quantities. Yeah, for finite systems is completely different. I mean, in safety, you can really evolve, you can calculate quite explicitly. You put some boundaries there. I mean, the large time limit doesn't exist because in safety, you're going to have infinite reflection. You could average over time, you're going to have a limit, but it's not that. It's something very different. So this is really specific to the limit of L infinite and then T large. More precisely, like T must be much smaller than some typical velocity times L, where here is CFT, much smaller than L. Okay. In fact, T strictly smaller than L will work. So, or smaller than 2L, I guess here. So yeah, so it's different for finite systems. And this comes to the comment that was made here. I would like my two halves to play the role of baths in some way, right? So they've got to be infinite so that things can be lost up there and up there. And it's what's happening here when you say the stationary state is that. I mean, here I've lost a lot of information because system is very large, so I just forget about information. So you want infinite system to be able to absorbs everything. And question of finite system is also valid. It's just different. Yes, no, indeed. So some local primary it's a bit more complicated. In fact, it will not be a sharp boundary first thing, because
I mean, just I want to know what's the station value, the stationary state.
Yeah, yeah, that is fine. So just very infinite time and just there, that you should be able to evaluate. Now you've got to write your primary, I mean, first of all, your initial state, you've got to write it in an appropriate sum of representations. I mean, you know, it's thermal state, but then there's non-trivial sum of representations now, and there's no non-trivial conformal blocks. So first you have to write that. Now time evolution, okay, so you know the boundary effects probably will not play a big role, and I'm not sure if the calculation has ever been done fully, but I would expect, well, I don't know. I mean, you're going to have something like that, but mixed with the conformal block structure. So, and I'm not too sure how the mixing is done.
One simple example would be like the singlet of the item model.
Yes,
like
yes,
epsilon.
yes. Well, epsilon is too simple. Yeah, but
The answer.
then it's just factorizes, yeah, directly.
So
Yes.
the answer. What's this dimension of the epsilon? Let's say we don't care about the number.
Yeah, I mean, maybe the, yeah, I mean,
the temperature.
yeah, I mean, sigma for instance, or epsilon. Yeah, sigma is 0, and epsilon is a bit too simple because it's a free fermion thing. So, and the free fermions really separate. In every model, the separation left and right mover occurs at the fermionic level as rarely, and so.
Okay, so let's take some singlet in a CFT.
Yeah, non-trivial CFT. Then you're gonna have, yeah. So temperature to some, you know, the dimension. Yeah. So you know, on the left and on the right you have that, and then as you evolve, you don't have that anymore, right? And you're gonna have it's not going to be a sum of something with left temperature and right temperature, because there's non-trivial conformal block structure, like there's non-trivial pairing between left and right sectors. And so you've got to take into account that pairing of the left and right sector. Now, I think each sector evolution would be straightforward, but that pairing is non-trivial.
So the effective temperature depends on the observable.
Yes.
That's not known, or
I don't think it's being calculated in general. Yes. It's a good question. It's a good, yeah, no, yes. It's a good question, obviously, yeah. But I don't think it's been. Then we've looked at fluctuation now, but yeah, that can be done. Yes. So actually, it's a good point. So the stationary state that I write like that, I mean, this is a stationary state I define as limit of local observables. So this is correct for a family of local observables. It is dependent on the family, the consistent family of local observables. And Vira-zero sector is a consistent family. It's a CFT. You can take that, and you know, OPEs include T's and T squares and all that. It's a closed family of observables, so that's okay. So you can take that as your theory and just stop there, and that's the correct state on these observables, but it's not on other observables.
for example, the singlet.
Yeah. Yes. So yes, I don't know. Maybe somebody's done it. I don't remember now.
But it's something the temperature depends on T log too, right?
Yes. And you can calculate it by left-right separation. You just have to take the pairing, the pairing structure between left and right sector. Which is important. The initial density matrix is like constant diagonal, right? So you have H bar, for 1, 2, 3, 4, 5 for whatever parameters you have, and that's your density matrix.
The 11, right? Almost the same.
Yeah.
Expansion.
Yeah. This I didn't discuss that, but yes, indeed. Yeah, that you could do. Yeah, I mean, you can do that even a level of hydrodynamics. Yeah. But yeah, so here I concentrate on the concept of density and currents, and then you have ET bar, and you could have the U1 current. One can do also U1 current when you have other symmetries, or SU2 or Weisman-Witten, similar thing, but simple. What you ask is a bit, I think maybe, yeah. Thank you.